Welcome to Chapter 6. Okay, so Chapter 6, not a lot of new stuff. Chapter 6 actually builds a lot on Chapter 5 and Chapter 4 and Chapter 3 a bit. So make sure you got your Chapter 4 and Chapter 5 learned already before you come to Chapter 6. Otherwise, you will say, how come got so many new stuff? Okay, make sure you go revise your Chapter 4 and 5 a bit. Okay, so look at this nice picture. A globe. Well, how does that relate? We'll find out. But I have one question for you. If you look at your screen, why is it glowing? Oh, because got battery ma, got battery, got light. Okay. Why does your phone have battery? Or your computer? Oh, because you charge, you plug in the socket there. Okay. Why does the socket have electricity? Because it's connected to the grid. Because the grid is connected, somehow the electricity is created and you can use it. You got aircon, you got light. All this have to do with work, energy, and power. Even something as simple as just me lifting up a water bottle, that is also some energy spent in my body, my muscles. If you take bio, you will learn about how our muscles, our cells spend energy, chemical energy, and create, enable us to do stuff. But anyway, a lot of systems around the world depend on how we treat energy, and we're going to look at what are the types of energy and what you can do with these energies. So conservation of energy. Just now I mentioned some type of energy. I mentioned got chemical, got electricity. Actually, you can just go Google search. You'll find a very nice list of energies and it looks something like this. This is just a rough idea of what types of energy there are. In physics, we will look at a bit of thermal energy, a bit of nuclear. Chemical, not so much. Electromagnetic, maybe a little bit. Sonic, not so much. Gravitational, yes. Kinetic, potential. Ionization energy, somewhat. Okay, but don't worry if you're like, wow, so much thing to worry about. At AS, in this chapter, we'll mainly be looking at gravitational, kinetic, and, well, other kinds of potential energy. The rest we'll save for later. So what's up with all these different types of energy? Well, the idea of conservation of energy is that energy cannot be created or destroyed, which means if you lose energy technically is not exactly energy loss in the world. It's more like the energy is converted to something else. That's why we say lose energy. Okay, so then some of you may go into existential question and say, if energy cannot be created or destroyed, then how come in the beginning of the world already got energy? Okay. That one's safe for another discussions. Okay, there are many views on where this energy appeared in this world. In the beginning, what happened? Well, you can ask me about it directly if you are curious to brainstorm. Where did all this energy come from in the beginning and why energy? Anyway, so the main idea is just remember, energy cannot be created or destroyed, but you can switch around. Means, let's say you lost kinetic energy because your energy has been transferred to thermal or something else. So you just convert here and there only, okay? So this world, energy is conserved. That's the main key point. So, next up, energy conversion is actually like a shortcut. In Chapter 3, I shall write aside. Chapter 3, we look at what we call the Stuva equations. There's 4 kinematic equations and we solve all kinds of problems with it. A lot of times, using this idea of energy conversion can save us a lot of time using the Stuva. So we actually don't need to use Stuva, we can shortcut with energy. We will see how to do that in some practice problems later. But first thing first, a refresher on what kinetic energy is. Kinetic means moving. So if you are moving, you got energy. Usually you will see people say EK, kinetic energy, is half mv squared. That's a reminder of what you've seen before in other courses before A-levels. EK, sometimes people will say KE, also the same thing lah. But EK means energy, kinetic. So anything that's moving has kinetic. I need to warn you about this. Moving is relative, because you see, I can be sitting here at this chair. So do I have zero kinetic energy? Well, technically speaking, I'm on Earth and Earth is moving very fast around the sun. So I'm actually not stationary. I am moving. But relative to the ground, relative to my room, I am stationary. So I say, oh, the ground is where I'm measuring my movement to, so I'm stationary. So I have, sitting on the chair, 0 kinetic energy. Okay, remember it's all relative. You need to choose where is your 0 reference point. Same thing goes for gravitational potential energy. We'll have another video on potential energy and look more detail about this. But a refresher, you may have seen it written as EP before, or GPE. Some courses will say that. But the main idea is just MGH. How heavy? What planet? How high? So, if I carry a water bottle this low, from the table move up, that's a certain energy I've stored in the bottle. If I move it even higher, I've stored even more gravitational potential energy in the bottle. So when I drop it, it's going to have much more kinetic energy because they're switching around. Okay, so these two are the ones we will encounter a lot in this chapter, and they can switch about. Okay, and we'll look at some examples of how you can apply these two ideas together. But before we go on to examples, what is the unit of energy? Your name Joule. I feel the name Joule is very cool. So, reminder, if you've forgotten, the unit of energy most commonly we say it's in joules. Joules, oftentimes J. Now these joules can be broken down into SI-based units, but we'll save that for a later video. So remember how just now I said that energy is like a shortcut to kinematics? If you look at this question, stone in freefall. A stone is thrown upwards from ground at the initial speed. Air resistance negligible. Okay, good. Don't need to worry about drag force and things like that. What is the maximum height reached by the stone? Now, if you think in terms of the old Stuva way, okay, let me draw a diagram. You have a stone, you throw up, it goes to the top, and then it stops. Maximum height. Okay, this is height. And that's where the velocity is 0. It stops moving, okay? Refresher. The initial velocity is, 15 meters per second. And as it goes up, it's actually slowing down, so it's having a deceleration of negative 9.81. Here I define up as positive, by the way. So acceleration is downwards. So when you see this kind of situation, you may think, oh, Stuva, can use Stuva, right? Can. If I say the bottom is a 0 displacement and the top is displacement of h, then I have v, I have u, I have a, I have s. So yes, you can use Stuva, v square u square 2as. But what if you want to think in terms of energy conversion? There's another way to solve it. In fact, for almost all the kinetic energy kind of question, not kinetic energy, kinematics kind of equation, projectile, ball, fly here, fly there, they also have a different way to think about it in terms of energy. And this is actually a shortcut. Energy usually is a bit easier because energy is a scalar. Anyway, so energy, a scalar. Conversion. Let's think about it in terms of conversion. When this ball is at the bottom, and we say that is 0 height, okay, so what's the total energy when it's at the bottom? In EI here is initial. So in the beginning, it's at height 0. We define that as our 0. So we have a mgh plus half mv squared, some velocity there, but since it's u, I will say half mu squared. Then, what is this thing here? There is no gravitational potential energy, so we say this is 0, because we say that is where 0 is. So all the energy that this ball has is just kinetic energy, purely kinetic energy. What is u? U is 15 meters per second. Then, as it goes to the top, it will reach a point where it will stop moving. Why? Because as it goes up, all the energy is being converted to potential. So kinetic become potential as it goes higher and higher to the top. Okay, eventually it run out of kinetic energy already. So at the end, the total energy is only no more kinetic, so only MGH left. Plus, no more kinetic already because velocity is 0 at the top. So I'll just write here 0 lah. Gone. So then you have MGH, which is what you're trying to find. Now remember I mentioned conservation of energy, right? So the total energy in this system of this stone cannot be lost. Therefore, energy before equals energy after this whole process of the end point. You need a start, you need an end, right? So, long story short, all the kinetic energy in the beginning has become potential energy at the top. M and M is the same, so we divide both sides by M. All left is half U square equals to GH. No more space already. So never mind. We write on the side half 15 square divide by 9.81 equals to the maximum height, which is, what's the maximum height? Calculate and see. So 15 square divided by 9.81. So you get about 11.4678. Okay, never mind. 11.5. Is this in meters? Yes, it's in meters. 11.5 I round up to 3 SF. If you want to round up to 2, also can. In fact, the answer will round up to 2 and you should get 11 only. But anyway, just remember, you're like, ayo, why you write out so much working, miss? Because this is the main idea of the whole chapter when you see energy conversion. Some of you may straight away jump to this step. That's okay if you know what you're doing. But you need to know how we come to that step. And that is because total energy before equals total energy after. Kind of like conservation of momentum, but for energy. Okay? So remember that. Another point people may ask is, hey miss, why the 9.81 here no negative one? Oh, because we're dealing with energy is scalar. And also direction doesn't matter. So this G value here in the thing is just gravitational constant. Just 9.81. No positive, no negative, it's just a constant. Okay? The only positive and negative that will be involved is energy loss, energy gain. But that's for later. So this is anything in free fall flying, you can apply this same idea of energy. So you need to use this two up here already. There's two ways to solve the same problem. Final add-on on this stone in free fall. If they ever ask you to draw a graph, don't panic. We have seen this before. So I briefly mentioned this in the projectile kinematics section as well. But if they ever ask you to draw a energy against time graph of this same stone in free fall, okay, so this stone you throw up, reach maximum height. So okay, so you start off in the beginning with no potential but full of kinetic energy. What was it? 15 meters per second. I can't remember what it was. Okay, maybe you throw up 15 meters per second. Okay, so you're going to start off with kinetic energy of 15 meters per second. Okay, but this is kinetic energy here. But your potential, you're starting off from ground. If you say ground level is 0 height, that's not a stone, that's 0 height. So you're going to start off with 0 potential energy, gravitational potential. Put the GP lah. So if you remember how displacement graphs look like, that's very similar to your gravitational potential energy because it is MGH. So your H is going up. Okay, so it's kind of looking something like this. That's your gravitational potential. So the stone goes up, stone comes down, bloop, back to the ground. So it's something like this. Ugh. So that is your gravitational potential energy. But what about kinetic? So gravitational potential, you're getting higher and higher, you gain potential, and you go down. So the same exchange has to happen with your kinetic energy. Okay, the total cannot exceed here. So kinetic is gonna go down and down and down. It gets slower, slower, no energy ma. The stone goes to the top, no more energy, then it stops. At the max height, velocity is 0 because no more kinetic energy. So that's at this point right here. This is at, well, the time at max height. Then your stone starts to drop down. Then the exchange happens. Now gravitational become potential. So, well, that's a good idea. Let me write this out. So on the left side, when your stone is going up, kinetic energy is becoming gravitational potential as it goes higher. Conversion. Then on the right side, when it's coming down, gravitational potential energy is becoming kinetic energy. Conversion, okay? You're going lower, gaining kinetic, losing gravitational. So your graph will be like this. Something like that. So you may see graphs that look like this. Just remember, one goes down, one goes up. Why? Because of conversion. And at every point, the total energy is the same. So total energy is this line right here. If you add up both points, they should equal to the same, because for this stone, energy has to be converted somewhere else. I mean, if you want to consider thermal energy, air friction, sure, then you have more lines to draw. But if we only consider gravitational kinetic, this is how the graph would look like. So that's a short tip. So this one is a railway engine, MJ17, one of those past year questions. We're starting off basics first to make sure you get this idea right. So just now we look at energy conversion. This one is slightly different. Railway engine, what's a railway engine? By the way, if you don't know what it is, it looks something like this lah. Basically, this picture is a modern version of the KTM or any kinds of train that you know. Okay, so it's railway engine. A lot of ideas in this chapter will be very real world. So they say piston lah, car lah, pulley, elevator, lift. So if you don't know what those things are, go and Google up, see a picture, you'll be like, oh, that thing is called escalator. Okay, a lot of real world machinery will come into this chapter. Anyway, a railway engine accelerates a train of total mass. Wow, tons. What on earth is that? Thankfully, they gave us a conversion. From rest to a speed of 75. From rest means at first the train is not moving. Then it moves. Okay. So that is your final velocity. Now you may think, oh, Stuva question. No. No need Stuva. We think of energy. Next part that some of us may find a bit strange is this word, useful work. How much useful work must be done on the train to reach this speed? Try it out if you have not. You can pause the video if you need more time. But useful work in this case means or is related to change in energy. Somehow the engine is doing work so that this train start with no kinetic energy, can start moving and reach a certain kinetic energy. So remember, work, when you see this word, is related to a change in energy. We will have more, in fact, a whole unit on work in the coming videos. But here, what can we do is, work done. Well, some people will use the word W for work. Can also lah, just don't confuse it with weight, because we also use W for weight. Anyway, work done is a change in energy. You start with at rest. Then in the end, you end up moving at a speed. Okay, so you have a E final, E initial, which means half mv square minus half mu square. Conveniently, in the beginning, everything is at rest, so that is our reference point. 0 is at rest for this case. So all we need is half, what's the mass of this train? 120 tons times 1000 kg times velocity. What is velocity? What's velocity? Oh, 75, yes. Minus 0, you can write out if you want to skip it, that's fine too. Okay, so 0.5 times 1200, 1075 squared. Woo, that's a lot of energy. If you remember, you calculated, if you see the ENG button, You can press the ink button and it will give you a standard form, means something like this. 3.375 times 10 to the 9. What's the unit? Joules, still joules. Okay, so the new idea here is this: work and energy. How do they relate? We'll elaborate more on this one, but keep in mind, work is a change in energy. You have a reference point and you change to something else. So what is the work done to get you up to that energy or below that energy? One more example. This last idea is about a hydroelectric station. By the way, in case you're not sure what it is, you see this a lot in rural areas where there are no electric grids. Basically, you have a lake or pond. The water will flow through a pipe down the hill, has to be downhill, into a unit which has like kind of fan blades, turbines inside there. So the water is going to turn the turbine and then come out. So when that turbine is turning, it's like an engine, it creates electricity for all the people connected to this hydroelectric station. Maybe your house might be powered by a hydro, I don't know. Depends on where you live. Anyway, what's the question here? A reservoir is linked by a pipe of uniform cross-section area. Okay, water flows from X to Y at constant speed. Okay, so some V is constant. Which statement is correct? Oh, which statement about the change of energy of the water? As it moves from X to Y. Oh wow, so many words. Okay, first things first, let's take a look. At X, it has the same constant speed. So you have some kinetic energy here and some kinetic energy at the bottom, and they are the same. Nothing lost, nothing gained. So based on that, if you go through and look, kinetic, the A says it gains kinetic, cannot be, wrong. B said it loses kinetic, no, kinetic is the same speed. Okay, how about gravitational potential? Your water at X is pretty high up. Then it goes down to some level. Okay, here's where your reference pointing can be fun. So if you say the ground is a height of 0, then this is some height of, I don't know how many meters, 22 meters, means you go -2 down. So you're decreasing height. Or if you want to define a little differently, you say, oh, I want up here to be 0. Can. If you go 2 meters down, then your height will be -2. Still the same thing, right? You just need to define where your reference point is. Anyway, for this case, I'll just say you have some gravitational potential. Let's use G. And you go down to another G, which is actually smaller because you have decreased in height. Okay, so your gravitational potential has decreased. Let's look at C and D. Loses gravitational, loses gravitational. Okay, so both C and D are possible. What's the weird thing here? Elastic potential? What is that? We will see a lot of this elastic in the coming sections. But basically, elastic potential is when you compress something, say a container, you compress it, and once you let go, it will point. It will kind of become its original shape. Or if you have a spring or some kind of rubber band, you pull it, the moment you're storing increasing elastic potential, the moment you let go, pia, it returns to original shape. Anything is squishy will have elastic potential energy. So in this case, how does water have elastic potential energy? Here's 2 points. Firstly, energy of the water has to be conserved somehow, it's transferring. So it's not likely that it will lose elastic and also lose gravitational. So I have a hunch C is wrong. Because in D, it loses gravitational, but it gains elastic. So okay, energy is converted to something else. Kinetic is out of the picture because it's just same. So likely this one. Actually, the answer is D in this case. Because up at X up here, the water is standard, normal there. But as you go down to Y, the water is more squished together. So imagine, how to say, water molecules, H2O, something like this. They're kind of apart, And then as you go down, they're all like pressed together. And they're kind of hitting each other more. There's one term we learned about this thing. What is that term in the previous unit? When you go from top and you go to the bottom of water, what increases? Pressure. Okay? High pressure, low pressure, all those stuff. So on top at X, you're going to have low water pressure. Go to the bottom, high water pressure. Which means all these water molecules are kind of like pressing against each other, pressing against the wall more. So it's kind of like stored elastic potential energy. Okay? Don't worry, not all questions are weird like this. I decided to pick the weirdest one to throw inside here so we can get started to thinking about different types of energy. Okay? So that's the weird question. So this is an overview of what to expect next. 6.1, we'll be looking at energy types conversion. So in this unit, we have a very general idea of what types of energy are there, what does it mean conversion and conservation. So conservation is total energy cannot be lost. Conversion is, it's not lost, but it's transferred from one form to another. Then in the next unit, you should be able to explain and calculate the work done. We talked about this very briefly in just now. Work done is basically change in energy. We will have different types: kinetic, potential, work done by gas, so you're compressing gas, and also work done by friction, so a car getting stopped by friction. Then the last unit will be 6.3 about power and efficiency. So we'll look at fun stuff: systems, engine, machine, circuit, pulley, I don't know, boat, car. Hey, that's not a car. I'll try my best to draw a car. Car, I don't know, crane, elevator, all kinds of stuff. But keep in mind, this is a very applied chapter. Meaning, I can show you 10 examples, but if you just memorize how to do them and don't really think about the concepts, then you won't be able to do any other questions other than those 10 I just showed you. So make sure, so these videos will largely be shorter, but please go try out the practice questions listed in the description below, because that will really help you to apply and think about different ways. Post about it, discuss with friends, and see how you can solve all these questions together. Okay, so make sure you know how to think about types, conservation, conversion, and we'll move on to 6.2, 6.3. Again, the main concepts of these are very short, almost simple, but application. You need to be able to think, apply, and practice. Got to train those muscles. Okay, so do those questions. I'll see you for 6.2.